Hello and welcome to DECA Tutorials. My name is Polycarp Ondieki. I'm a teacher of physics and I've been teaching for the past 8 years. Today I will be talking about Kirchoff's first and second laws. These two laws look at the flow of current in an electrical circuit. Kirchoff was a German physicist who contributed to the understanding of electrical circuits. Now, let's look at some of the definitions as we begin. These terms are very important for us when solving a circuit diagram. Solving a circuit diagram simply means finding the voltages and currents of all the components in the circuit. Let's start with a junction. A junction is a point where three or more wires are connected to each other in a circuit. The second term is a branch. Assume you have two junctions, A and B, and in between you have wires and components. This is what we call a branch. A branch connects two junctions to each other. The last term is the loop. The loop is the connection of all the components and wires in a complete cycle. Now let's start with the Kirchoff's first law. Kirchoff's first law states that the sum of all the currents flowing into a junction is equals to the sum of all the currents flowing away from that junction. Now let's consider a junction with 5 wires. 3 of these wires are carrying current into this junction. Let's call them I1, I2, and I3, where I is the symbol for current. 2 of these wires are carrying current away from this junction, and let's call them I4 and I5. Going by this law, the sum of I1, I2, and I3 must be equal to the sum of I4 and I5. In this first law, charge is conserved. Now let's talk about Kirchoff's second law. Kirchoff's second law states that in a complete circuit loop, the sum of all the EMF is equal to the sum of all the potential difference in that loop. EMF simply stands for electromotive force, which is the energy provided by the cell or a battery. On the other hand, PD, that is the potential difference, is the energy needed to move a charge from one point to another in an electrical component. This Kirchoff's second law is equivalent to the conservation of charge. Now let's look at an example. Calculate the currents I1, I2, and I3 in the circuit shown. What you do first, identify the junctions in that circuit. Here we have junction A and junction B. Then you assign each junction the current going into that junction. We are going to use junction A in our case to find the value of I1, I2, and I3. I1, as it is indicated, it's flowing from voltage V1 to junction A. I2 is flowing from voltage V2 to junction A. And I3 is flowing away from junction A. Using Kirchoff's first law, we know that all those currents going into junction A, I1 plus I2, must be equal to all those currents going away from junction A. That is I3. Let's call this equation 1. We select a closed loop so that we apply Kirchoff's second law. I'll choose loop 1. I assign this one L1 for loop 1. And I'll choose loop 2. I assign this L2. So for loop 1, applying Kirchoff's second law, we have the EMF in loop 1 is 10 volts. This must be equal to the potential difference in loop 1. So we have R1, resistor 1, 10 ohms, and current through it. So there is a potential drop of I1 times 10 ohms, which is 10 I1. Then we have R3, resistor 3 of 40 ohms. The current through R3 is I3. So the potential drop will be 40 I3. So let this be the second equation. Now, using loop 2, the EMF is 20 volts, and this must be equal to the potential drop in R2 when current I2 goes through it is 20 I2 plus the potential drop in R3, which is 40 I3. This is third equation. Now we have three equations with three unknowns, so we need to solve them simultaneously. Start from equation 2. That is 10 I1 plus 40 I3. You can see 10 is common. So we have, if you divide all through by 10, we have 1 is I1 plus 4 I3. Make I1 the subject of the equation. We have I1 is 1 minus 4 I3. Let's call this one equation 4. From equation 3, we have 20 equals 20 I2 plus 40 I3. Here, 20 is common again. So divide all through by 20, you get 1 is I2 plus 2 I3. Make I2 the subject of the equation. We have I2 is 1 minus 2 I3. So let that be equation 5. If we substitute equation 4 and 5 into equation 1, we have 1 minus 4 I3 plus 1 minus 2 I3 equals to I3. So we put like terms together. Here we have 2 equals to 4 I3 and 2 I3 to the other side. You have I3 plus 4 I3 plus 2 I3, 7 I3. So divide by 7 both sides. You have I3 is 2 over 7, 0.29 amps. Now we have I3, we substitute into equation 4 so that we get I1. So I1 is 1 minus 4 into 0.29. So if we use our calculator here, we get 4 multiplied 1.16. So minus 1 minus 1.16 is minus 0.16 amps. Now the significance of the negative implies that the current is moving in opposite direction of the route that we assign. So using now equation 5, we can get I2 is 1 minus 2 multiply I3. I3 we solved as 0.29. So using our calculator again, 1 minus 0.58, the answer is 0.42 amps. So here we have the three currents in the circuit. We have I1, which you've gotten minus 0.16 amps, I2, which is 0.42 amps, I3, which you've gotten 0.29. Thank you for watching, and I hope you've learned something from this video. Please like and subscribe to this channel for more videos like this. Until next time, thank you.